Okay, one thing that I want to add to Khan Academy's exponent is exponential decay and exponential growth. If our exponent equation is y equals abx, where b is our exponential term with the x as our exponent, a is always going to be greater than 0. If b is between 0 and 1, so if that term, whatever's being raised to some number, is between 0 and 1, that means it's a half, a fourth, an eighth, 0.00082, then it will always be decay. If b is greater than 0, sorry for those scratch outs, if b is greater than 0, then it's always a growth. So all you're looking for you to be able to tell growth or decay, find whatever's has an exponent, whichever term has an exponent. If it's greater than 1, if it's growth. If it's between 0 and 1, it's decay. For instance, here I have y equals 1/5 x. Well, 1/5 has an exponent, so that's our b. Well, b is not greater than 1, but it is between 0 and 1, so this would be exponential decay. We also have, what about this one? Y equals 3/4 to the x. This is our a, because there is no exponent. Here's our b with an exponent of x. I look at b. Is b greater than 1, or is it between 0 and 1? Well, b is greater than 1, so this would have to be growth. That's just the difference between growth and decay. Looking in the book, you can see an easy chart that shows you. This graph here shows you where exponential growth versus exponential decay going down like that. Okay, the other part of section 1 that I want to talk about is solving exponential equations. The biggest thing to remember for solving exponential equations, if I have two exponents, b to the x equals b to the y, this can only be true if and only if x equals y. So x and y have to be the same exponents for these to be congruent. So I would have to have 2 to the 3 equals 2 to the x. So what would x have to be? For these to be the same number, well, obviously x here has to be 3. These two terms have to match. For me to have 2 to the x equals 2 to the 8th, the only way that this works, 2 to the x equals 2 to the 8th, is if x equals 8. And that's what we're going to be doing. This is the easy form of it. Of course, we're going to take some examples that are a little bit harder, but we still do the same thing. Our first example that we're going to look at is 3 to the 2n plus 1 equals 81. Now, I don't have an exponent here. I have this number 81, and I have an exponent of 2n plus 1. Well, that 2n plus 1, for this to be true, has to somehow equal up to 81. The way that we do this, you leave the one that has the exponent. So leave the one that has the exponent, and you switch the other one to have the same base. They have to have that same base, that same b. So for us to do that, we have to say, what 3 to what power gives me 81? Well, 3 to the 4th power gives me 81. 3 times 3 times 3. You can use a factor tree to figure that out. I can do 9 times 9. And we can say 3, 3, 3, 3. And I would say, 3 to the 4th. I want 3 to be my number. So that's what I'm aiming for because I need to have the same base. So now I have let me rewrite that. 2n plus 1 equals 3 to the 4th. Now I have the same basis, and all I do is set my exponents equal to each other. Remember, for this to be true, our exponents have to be equal. So I'll just say 2n plus 1 equals 4. Then we solve. Minus 1, minus 1. 2n equals 3. Divide by 2, divide by 2, n equals 3 halves. I'll give you some more examples of those later.